Welcome back. Today we're going to talk about balanced search trees, which will lead us to an ultimate symbol table implementation that can provide fast performance for all the symbol table operations we've looked at, guaranteed. So here's a review of where we were with symbol tables. We took a look at the last time at the binary search tree, which if things are well modeled by random insertions have great performance. They get search and insert done in time proportional to log base 2 of n, and they support ordered operations. But really, our goal is to have these operations be guaranteed to take time proportional to log n, because we don't have control over the order of operations, and they may not be random at all. And in fact, in many real applications, they're not very random. So that's what we're going to look at now, is try to find an implementation that can guarantee to be fast for all the symbol table operations. That's our challenge. So what we're going to talk about to do it is a algorithm that actually a pretty old algorithm called 2-3 trees in a particular implementation that requires very little code called left-leaning red-black BSTs. And then we'll talk about a generalization called B trees. And these methods are all widely used throughout our computational infrastructure. To start, we'll talk about 2-3 search trees, which is a model that underlies the concise and efficient implementation that we're going to look at. So a 2-3 tree is a way to generalize BSTs to provide the flexibility that we need to guarantee fast performance. And the idea is very simple. We allow 1 or 2 keys per node. That is, we allow for the possibility of something called a 3 node that can hold 2 keys, but then it has to have 3 children. In a regular BST node, a 2 node, we have 1 link for the keys that are less than the key in the node, and 1 link for the keys that are greater. In a 3 node, we need 3 links, 1 for less, 1 for between, and 1 for greater. Another property of these 2-3 trees is that we're going to have perfect balance. That is, every path from the root to a null link is going to have the same length in a 2-3 tree. So as I mentioned, the symmetric order is part of the definition of a 2-3 tree. Every 3 node has 3 links and 2 keys. The left link is for the keys that points to a 2-3 tree with the keys that are smaller than the smaller of the 2 keys in the 3 node. The middle link points to a 2-3 tree that contains all the keys that are between the 2 keys. And the right link points to a 2-3 tree containing all the keys that are larger than the larger of the 2 keys in the 3 node. Okay, let's take a look at a demo of searching in a 2-3 tree. So say we have this 2-3 tree here, and we want to search for whether or not H is one of the keys in the tree. So we start at the root, compare the search key against the key or keys in the node, and follow the link corresponding to the interval that we know must contain the search key by the definition of the tree. And then we recursively continue the search. So if we're looking for H, it's less than M, so the only place it could be in this 2-3 tree is in the 2-3 tree on the left link, so we follow the left link. Now we compare H with E and J, and in this case it's between, so now we're going to take the middle link. That's the only place that H possibly could be. And in this case, that node, one node 2-3 tree contains H, so that's a search hit. Let's take another example for unsuccessful search, a key that's not in the tree. As usual, we start at the root. It's less, so we go left. It's less than both keys, so if it's in the tree, it would have to be on the left link. And it's between those 2 keys, so if it's in the tree, it would have to be on the middle link. And that link is null, so that's a search miss. So the search is a natural generalization of the search in binary search trees. Now what about inserting? Well, it's a similar type of strategy as with regular binary search trees, except that we manipulate the 2 and 3 nodes to keep perfect balance in the tree. So the easy case is if the key winds up in a 2 node at the bottom, like this one. Suppose we're inserting K. K is less than M, so we go left. K is greater than both keys, so we go right. K is less than L, so the search ends at the left link of L. And to perform an insertion, all we need to do is replace that 2 node with a 3 node containing K. Now K is inserted into the 2-3 tree and it satisfies all the rules. Now if we're inserting into a 3 node at the bottom, we have to do more work. And specifically, the work we do is we add the key to a 3 node to create a temporary 4 node and then split up that 4 node and move its middle key into the parent. So let's see an example. If we're going to insert Z into this tree, it's greater than M, so we go to the right. It's greater than R, so we go to the right. Now it's greater than X, and that's a null link to the right of X, so the search ends there, and what we'd want to do is insert Z into that 3 node. And the way we do it is first make a temporary 4 node that replaces that 3 node. And then that's not a 2-3 tree because it's got that one 4 node with 3 keys and 4 links. But what we can do is split that 4 node and pass the middle key up to its parent. So split it into 2 nodes and pass the middle key to the parent. That's kind of a magical operation, and believe me, it's easier to get it done in the implementation than the graphics. But now you can see that that local transformation on the 2-3 tree completes the insertion. Now, if that parent were a 3 node, it would become a temporary 4 node and would continue the process moving up the tree. That's a demo of search and insertion in a 2-3 tree. So let's look at a double split like that. So say we're inserting L into this tree. So it goes down to the middle and winds up needing to be inserted in the 3 node in the middle. So we're going to convert that into a 4 node. Now L's the middle key of that one, so we're going to split that 4 node into 2 nodes and move L to the parent. The 4 node had 4 links, and the 2 nodes have 4 links, so nothing has to be changed below. And then this insertion into the parent changed it from a 3 node into a 4 node, essentially adding a link because of the split with the 2 nodes where there was only one 3 node before. But now that's not a 2-3 tree, so we have to split again. And in this case, there's no parent, so we create a new one, and the height of the tree increases by 1. That's the only time the height of a 2-3 tree changes. When the root splits, the height increases by 1. So that's a demo of insertion into a 3 node at the bottom in a 2-3 tree that percolates all the way to the top. Now let's look at constructing a 2-3 tree from an initially empty tree. So if we start by just inserting a key, well, that just creates a 2 node containing that key. And that's a legal 2-3 tree, so we're fine. Now inserting E into that, well, it's going to be, if it's in the tree left of S, that's a null link, so we need to convert that 2 node into a 3 node. Okay, and that's the legal 2-3 tree, so we stop. Inserting A into that, we convert that 3 node into a temporary 4 node, but then we need to split that 4 node, moving E to the parent, and that creates a new root node and increases the size of the tree by 1, but now that's a legal 2-3 tree, so we stop. Insert R into that, it goes to the right of E, convert into a 3 node. Now insert C into that, goes to the left of E, has to be joined with A into a new 3 node. Again, that's a legal 2-3 tree, and we stop. Now we insert H, that goes to the right of E, that 3 node gets converted into a 4 node. That's a temporary 4 node, we split and move R to the parent. Now that parent's a legal 3 node, and there's nothing more to be done. We have a legal 2-3 tree. Insert X, it's bigger than R, goes to the right. There's a 2 node, there's room for the X. Insert P, That goes between E and R, the 2-node containing H. Right link is null, so we convert that 2-node into a 3-node. And now we have a legal 2-3 tree. Now you can see this next insertion is going to cause some splitting, wherever it is. So insert L, that's between E and R, so it goes in the 3-node containing H and P. We convert that into a temporary 4-node, split that 4-node, moving L to the parent. Now that parent's a 4-node, and that has to be split, and we create a new root node, and then the height of the tree grows by 1. And that's a legal 2-3 tree, so we stop. So those local transformations, converting a 2-node to a 3-node, or converting a 3 to a 4, and then splitting and passing a node up, those are the only operations we need to consider to get balance in our search trees. All right, so as I've mentioned, and this diagram shows, the splitting a 4-node in a 2-3 tree is a local transformation. It only involves changing a constant number of links. So in this example shows the general situation when the 4-node to be split is the middle link, but the same is true if it's a left or right. And those 6 subtrees drawn could be huge. They can contain millions of keys, but it doesn't matter what they contain. We don't touch them at all, nor do we touch anything above this node in the tree until a split happens. So the transformation that splits that BCD node and inserts the C into the 3-node at the root just involves making that 3-node into a temporary 4-node and making that 4-node into 2 2-nodes and adjusting the links appropriately. Just a constant number of operations, and that's why this operation is in general efficient. So let's look at just the global properties that these manipulations preserve. The 2 things that are critical is that in a 2-3 tree we always have symmetric order. That is the order that we defined for 2 nodes and 3 nodes. And we also have perfect balance. The distance from the root to the bottom is always the same. And to prove that, we just need to show that each transformation maintains symmetric order and perfect balance. And these are all the possible transformations that we could do. If we split the root, then that's what happens at the root. And if there was perfect balance before, there's perfect balance after with the height 1 bigger. If the parent was a 2-node, then the transformation is a local transformation. And if you look at where the links are, then it's easy to see by induction that if there was perfect balance before, there's perfect balance afterward, because we didn't change anything about the perfect balance in any of those subtrees. And that's true in every case. If the 3 nodes at the right, then this one is 1 higher and those 4 are 1 lower, and afterwards it's the same. If there was perfect balance before, there's perfect balance afterwards, because we didn't change the height of any nodes. We just moved things around locally within nodes. And this is when the parent is a 3-node, then there's the 3 cases. If we split at the left, split at the middle, and split at the right. And again, changing the 4-node to 2 nodes and adding links. If there was perfect balance before, there's perfect balance after, because we didn't change the heights of anything else in the tree. So our operations maintain symmetric order and perfect balance in a 2-3 tree. So that's going to give us a very easy way to describe the performance. All our operations have cost that's proportional to the path length from the height to the bottom, and every path from the root to a null link has the same length. How long can those paths be? Well, it's not hard to see that in the worst case, if they're all 2 nodes, that's the longest they could be. It's log base 2 of n. And if they're all 3 nodes, it would be log base 3 of n, which is less. It's about 0.63 log base 2 of n. So all the paths in a 2-3 tree with n nodes have to have length between those 2 bounds. And those are pretty small numbers. For 1 million nodes, that's between 12 and 20. And if it's a billion nodes, that's between 18 and 30. Those are remarkably small numbers. So we're going to have guaranteed performance, even for huge databases. We're going to be able to guarantee that we can get search and insert done with just 18 to 30 operations. That's quite remarkable, really. So here's what our table will look like when we finish the implementation of 2-3 trees. Every operation is guaranteed to be a constant times log n. Now the constant depends on the implementation, exactly what kind of manipulations we need to do to convert 3 nodes to 4 nodes and so forth. But it's easy to see from the demos and the diagrams that those are going to be constant. Guaranteed logarithmic performance for all operations, which is certainly what we want in a symbol table implementation. Now, what about the implementation? Well, we're actually not going to talk about a direct implementation of 2-3 trees because it's kind of complicated. It's cumbersome to maintain multiple node types. You might need multiple compares to move down the tree. If there's a 3 node, it takes more compares than a 2 node, so it's complicated to analyze. We have to keep track of links as we go up and down the tree to handle the splitting, and there's a lot of cases. I drew all the cases, and there's whether you're splitting into the middle of a 4 node or the right of a 2 node, there's just a lot of cases. So you could do it, but we're not going to because there's a much easier way. So that's 2-3 trees, a model for implementing balanced trees and guaranteed logarithmic time.